Okay, so for this one here, we no longer have horizontal only, horizontal velocity. What we have is projectile at an angle. So if you look at that in terms of the diagram that we have to draw, it looks something like this. Okay, we're coming out at 50 degrees, and our initial velocity is kind of like our magnitude of a vector, in this case 200 meters per second. So if you want to look at this in terms of vectors, let's take a look here. Okay, we're gonna break this vector, whose magnitude is 200 and angle is 50. We're gonna break that into its x and y components. So the x component here, y component here, and if we look at the cosine of 50, we get x over 200, which really tells us that the x component, the x portion of that 200 meters per second, is 200 times cosine of 50. Right? And our y is 200 sine of 50. Yeah, if you do sine of 50, it's opposite over 200. So it's just like cosine, except we switch our y, our x and y. So basically, if you take cosine of 50, well, cosine of 50 and sine of 50, they're both close to, what, I don't know, a half maybe. So it's basically breaking it up, saying that yes, the overall velocity is 200, but the force of that 200 just horizontally is 200 cosine 50, so about half that, and the force of that 200 meters per second vertically is 200 sine 50, or about half of that. So in terms of our x1 and y1, for our parametric equations here, remember x1 is always your horizontal component of your velocity, so 200 cosine 50. It's the horizontal component times t. We don't have any other wind taking into account. Gravity is straight up and down. So we're done with our x1. The y1 starts out 200 sine of 50 times t, and then we have our gravity, 4.9 t squared. And we need to look and see if there's any indication of a starting height. And since there's not, you just assume that it was fired off from the ground. So let's put x1, y1 into our graphing calculator. I've actually already done it, and what you see, we get 200 times cosine 50 times t, and in the y component, same thing, 200 but sine 50 times t, and then minus 4.9 t squared. Alright, so take a look at our graph, and clearly our window is not quite right. What this is telling me is, we know we start at 0, 0, but our graph here, you can tell our x-axis is nowhere near long enough. And even our y-axis, the height on this is not very good. So the first thing I want to do is change our x-min and x-max. So having done this problem before, I'm going to tell you that looking at a problem that says you start at 200 meters per second, even if this thing travels for 10 seconds, that's a long ways. So when you go to this window, let's just say we just go for 2000. All right, I'm not changing anything else. I want to see where we're at. All right, you can see that we're still only seeing the left side of our graph. So 2000 still isn't quite enough. So let's go 4000 and see what happens. Still not enough, because we're still seeing our graph go up, but we're not seeing it come down. So we'll go to 5000. Alright, so while we're working on that, We still can't see it, but let's at least get our y max changed. Clearly our x max is very large, so that means I'm going to ramp this up. I'm just going to go right to 2000 and change that. Okay, good. So here's another reason we can't see the rest of our graph is we only iterated our function from 0 to 10 seconds. So let me go up and let's look at that. Remember, we only told this thing to evaluate xy plot, our xy coordinates, for 10 seconds. What this graph is telling me is that after 10 seconds, the bullet or the cannonball, whatever it is we're firing, is mid-air after 10 seconds. So let's see, 10, 20, 30. Let's just jump up right up to 60. That way we know we have plenty of time. So now my graph is going to it should extend, and there we have it. And oddly enough, our x max is within range, 5,000, and so is our y min, y max at 2,000. So our problem wasn't that our window wasn't big enough, it's that we had not evaluated our function for a long enough time. So now that we have, let's go back and see what the question was. The question at hand is, well, there's a couple. First things first, let's go orange here. This here function gets put right there, and our y function gets put right here. So when it's asking horizontal and vertical component, we're just going to take our x1 and our y1, and this would be 200 cosine 50. Now remember, we're not putting t on it because that's our function. This is just the horizontal component of the vector, and this is the 200 sine 50. Alright, so I'll at least get rid of those arrows for now. So we've covered that. So the next three questions: how long is the projectile in the air? What's the horizontal distance it travels? And the maximum height it reached. Well, let's do the maximum height just because we can. So looking at this graph, letting it come up, we know that right here in this corner is 0 seconds. Right here in this corner, well, actually, we just know that this is 5,000 feet. We knew that this was about 10 seconds to about right here. So if this is 10 seconds worth of time, I'm going to start my tracing at 20 and see how close we are. Okay, so we are too far. So what we have to do is go back. Let's go to 15. Okay, so we're a lot closer. What we're looking for is that y value to peak and then come back down. So 1,187, 1,187 again. It looks like we pretty well peaked out right at 1,197. So what we need to do is maximum height to the nearest meter was, let's go back, 1,198 meters. Okay. Now, the other two questions are answered at the same time. If this is 15.5, let's go right out to about 30 seconds. So if you look at 30 seconds, we're still 186 feet above ground. So I'm going to keep moving that thing until our y value becomes 0. We're at 55, 40, 25, 10, -5. Okay, so somewhere between 31.3 and 31.2 is where we went, which is around 4,000 feet. So here's what we're going to do. We're going to do 31.2. We're going to take our window and go 0.01 seconds, graph this, and I'm going to pause because this is going to take a minute to load. So I will just pause the recording here. Alright, so change of plan. Instead of graphing that and tracing it, it's going to be a lot faster and a lot more effective if we go to a table instead. So instead of graphing that, at least the graph will give us an idea, and I do encourage you to use the graph with an iteration or a t-step of 0.1, but as soon as we start going to like a table or a t-step of 0.01, what I would recommend is jumping to the table. So what we found was that at 31.2 seconds, it was between 31.2 and 31.3 seconds. So that was where our critical point is, where we crossed from above ground to below ground. So table start, you're going to type in that lower bound, that 31.2, and then you're going to make your table, your delta table. That's just like the t-step. So our t-step will be 0.01. So what we're going to do is, instead of making our computer or calculator graph that, we're just going to list out our table and see how much quicker that just came up. We're going to now look and notice, here's our 10 seconds at 31.2, sorry, not 10 seconds, 31.2 seconds we were 10 feet above the ground. 21, 22, 23, we're still above ground. So right there at 31.26 and 27. So between 31.26, excuse me, 31.27 is where we hit the ground. That tells me then that somewhere between 4018 and 4020 is when we, as far as like distance from the origin, 4019 was our distance. So if we go back, the question at hand was, time the projectile is in the air was, what did I say, 4,000, oh, I'm sorry, not that, 31.2, we can go 31.3, 31.3 to the nearest second, 31, so 31 seconds. So I would say then our next step, our final step, is looking at the horizontal distance traveled. That was that 4,019. And if you look at it, says just to the nearest meter. So yeah, 4,019. Again, make sure you have your labels for seconds and meters. I guess this, if we wanted to put a unit on there, that would also be meters. We have our components, we have our units, 31 seconds, 4,000 meters, maximum height. So that is how you do a problem like that, where your projectile is being launched at an angle.